Hello students. Today we will discuss about defining computer architecture. So last session we were discussing about the performance growth during the past years, and we have seen several classes of computers based on general features as well as parallelism method. And today we will see in detail about what is actually a computer architecture and what are the different requirements for defining a particular computer architecture. So when we consider about a computer architecture, or when we are going for preparing an architecture for a new computer, we need to consider a person who is called as a designer, or who can also be called as an architect. Okay, so computer designer is a major person who will decide all the design aspect of the computer that is to be created as a new system. So who is a designer? Who determines what are the attributes required for a new computer. So he will decide the various attributes requirements for a new computer that is to be generated. Okay, then he will design a computer to maximize the performance. So he need to consider some features like it should have more performance, it must be energy efficient, and in the meantime, so two major features like performance and energy efficiency must be there when a designer tries to propose a new system. Now in the meantime, he need to consider the cost, the power requirement, as well as the availability constraints. Cost, as we know, we should have more performance with less cost for any product. Similarly, the power requirement also must be less when we are buying a new computer, because if it takes more power, we cannot say that it is not a better system than the system that we were using previously. Similarly, the availability also, availability in the sense all the device memory availability and even primary memory, secondary memory, all the availability features must be satisfied with the newly designed system. So the designer need to consider all these factors when he is actually trying to make a design on a new system that is to be created as a new one or a new version of an existing system. So a computer designer, during his design, he is actually passing through a number of stages. So we'll just look at those stages. There are actually four stages. First stage is called as instruction set design. Instruction set design, that is the stage where the actual instruction set, which type of instructions that system need to follow, the basic internal assembly instructions set, that format, what are the different instructions that can be used with that particular computer, how many bits can be taken for the manipulation or any similar operation. All these factors to be considered, and accordingly the designer need to go for an instruction set design. That is the primary stage. Then the second one is the functional organization. The functional organization of various elements present in a computer system. So we are having various processors, ICs, memory devices, RAM and other memory devices. All these are, then power supply, all these are connected to the system for the final means product. So they need to go for a functional organization, how these devices, different elements are organized within the computer system. So we need to consider which element comes first, which element to be connected to a second element, and how these different ICs, different pins are being connected. So all the structures regarding the functional ordering of all the elements must be decided during the second stage, that is called as functional organization. Similarly, next one, one of the major stage is called as logic design. It is related to the IC, integrated circuit logic design. That is related to the transistors, how many transistors are allowed to be added into an IC, and how these transistors are compatible, or how they can be fixed within a single block or within a single chip. So all the logics behind that integrated circuits will be designed, because when we go for a new processor, there will be a lot of differences in the design of logic within that particular processor chip. So every time we are not using the same chip as in the previous system, so they need to have some more logic level implementation to be done on the newly created integrated circuit processor. So logic design is also one of the major stage of computer architecture design. And finally, we should have the implementation of various elements. Implementation actually having some more units where the final how we can implement. So implementation design must be generated by the designer or architect. So he need to consider the exact design of an IC, how an IC can be designed. Earlier it was the logic of IC will be designed. Now how this IC can be designed, in which format, which shape, and how much compatible, how many pins, how many transistors, etc. All these are considered during the real implementation of that IC design. Then comes the packaging. Packaging means how these transistors can be packaged within a single unit called as IC. So how this can be added into that single block or within that single boards, and how this can be packaged, how this can be covered, how this can be placed within that particular boards. That is called as packaging. So IC design, the design of IC, then packaging. Packaging means how the elements can be packaged, how it can be covered, how it can be properly placed within a particular boards. Similarly, power, the various power supply, the requirement for power for each element. So different ICs, different pins, different elements actually require some power supply. So according to the requirement of each of these devices, they need to go for they should maintain a system, power supply system, to provide the exact power supply requirement for each of the elements present in the integrated circuits as well as other devices. So the designer need to consider that also every element, every pin require how much power supply. So that is to be decided. And finally we should have a cooling mechanism that will actually decide the cooling, means the usage of a fan within the computer system, which is actually used as a cooling system. So what type of fan can be used for making the system cool? If the power supply rise, means if it consumes more energy, automatically there is a chance of having more heat being produced. So that situation we always require some cooling mechanism. So how the cooling mechanism can be implemented, that will also be decided during the implementation phase. So these are the duties of a computer designer. He will overall he will decide the different attribute requirements for a new computer. Accordingly, he will try to design a computer with maximum performance and maximum energy efficiency, with less cost, less power, and more availability constraints. And the different stages for those design consist of instruction set design, functional organization, logic design, and finally implementation. And implementation again consists of IC design, packaging, power, and cooling requirements. Then we will see one by one. First one is instruction set architecture, which is the major part of the computer system design. Instruction set architecture that deals with the programmer visible instruction set, because the instruction that comes in between the user and the system is actually in the form of an assembly language instruction. So how the user can communicate with the processor with the support of only instruction. So what is that instruction? How we can decide what type of instructions we can use, what are the different types of instructions that can be used, and how these instructions can be applied and how this can be implemented within the system. All these are actually coming under the instruction set architecture. So under this instruction set architecture, we need to consider various elements that is related with instruction set architecture, which is generally, it is shortly called as ISA. Most of the time it will be used like ISA, instruction set architecture. So inside this we will be discussing about the different classes of instruction set architecture, the different types of instruction sets, then similarly how the memory addressing can be done, then what are the addressing modes available, how these memories can be referred. So different addressing modes are being used. So we look at some of the addressing modes used in various processes. Then what are the types and sizes of operands, what types of operands and what all sizes we can use with our instruction, those details to be considered. Similarly, what are the different operations possible with an instruction, an instruction set architecture. So we will look at various operations. And next one is a separate category of operations which is called as control flow instructions, which is used for branching and other movement from one location to another location during the execution of a program. And finally we look at how the instruction can be encoded, how this instruction is actually placed into a computer system, in which format. So when we actually enter the instruction, how this instruction will be stored within the memory for its further operations. So these details to be discussed means we need to have some discussion on all these points regarding the instruction set architecture. So classes of ISA, memory addressing, addressing modes, types and sizes of operands, operations, control flow instructions, and encoding and instruction set architecture. We will see one by one. First one is classes of ISA. So generally the instruction set architectures are classified by using or classified as a general purpose register architectures. So most of the instruction set architectures are classified as general purpose register architectures. So they will be using some registers and memory. So these classification, the operands are either registers or memory locations. So within the instruction, either we can use 2 registers, 2 or 3 registers, or we can use some memory addresses and these two. So all the instructions that uses these registers and memory are actually coming under general purpose register architectures. So most of the processes follows general purpose register architectures. So we'll see one example, 80x86. Examples like 80386, 80486. They actually consist of 16 general purpose registers, and in the meantime it also consists of 16 floating point registers. So for normal integer numerical values, and for floating point we are using separate set of registers. So this high order means from 8085, then we had the high order 80386, 486 and its successors. So there we are using different set of general purpose registers that depends on the size also. So sometimes, so in 80x86 we are using 16-bit general purpose registers and 16 floating point registers. So that much registers are available for storing the elements. So another processor architecture is Mips architecture, which is called as a microprocessor without interlocked pipeline stages. Mips, so which was a commonly used processor in earlier years. In the previous graph where we were discussing about the growth in performance, you can see Mips architecture in the earlier stages of 80s and all. So which is actually microprocessor without interlocked pipeline stages architecture, Mips architecture, which is a special category of processors like 80x86. So the property of Mips is it uses 32 general purpose registers and 32 floating point registers. So it uses small number of registers for both general purpose as well as for floating point operations. Then this general purpose register architecture can also be divided into two. They are also of two type. Generally they are used in two different situations. One is register memory ISAs, where we can access the memory by using any instruction. Means we can use several instructions for accessing the content of memory with the support of register and memory. So the instruction will be consisting of both register and memory, and these register and memory can be used with many of the instructions. So all the instructions can access the register and memory directly, and accordingly we can access the data of register and memory. But a second category that is called as load store ISA, where memory access is possible only by using load and store instruction. So the processors like ARM and Mips, these two architectures, these two processors follows load store ISA. For memory access we should use load or store instruction, but here in register memory ISAs any instruction can directly access memory. As part of the instruction we can directly access the memory or register, but for ARM and Mips architecture we should use either load for loading from the memory and store instruction for storing into the memory. So for all memory access we require load or store instruction in the case of ARM and Mips. So these two are the category of general purpose register architectures where we use different, means these two are different type. Some of the processors follows register memory ISA architecture, some of the processors follow load store ISA architecture. So all these are actually coming under general purpose. Most of the processors are following only general purpose register architectures. So next we will see memory addressing. The second point is memory addressing. So how the memory will be addressed? How the memory will be addressed means, so what is actually the meaning of address? Address means if you want to find out a particular address, means an address will be given like a house number, house name, then the post office, street, etc., and that addressing. So based on that address we will find out the address of a particular house. Similarly, if some contents will be available within the memory, so how this memory will be addressed? So most of the processors like 80, x86, ARM, Mips, etc., all of them are using byte addressing. Byte addressing to access the memory operand. What is this byte addressing? Byte means it is a combination of 8 bits. So assume that we are having 2 bytes available. So this is the first byte and this is the second byte. So here first byte it will be having 8 bits available. 8 bits available. That is the first byte. Second byte also consists of some 8 bits. Okay, so normally if I want to place a data, it should be placed in first byte, then if the memory is not enough for that data, the next byte will also be taken. So the data will be spread across the first and second byte. Okay, so if the data is very small, it can be used for placing only in the first byte, so that any situation, if somebody is trying to access that data, it can access, it need to access only the first byte. Now if the data is present in the second byte, the instruction will directly access the content from the second byte alone. But sometimes the data may be wrongly placed by mixing the space from 2 bytes. There are some situations, not in these processes, some other processes, where they are not using byte addressing. The problem is the first 8 bit, then next 8 bit, the data is residing with the some portion of first byte as well as some portion of the second byte. Now the problem is, if the instruction need to access that data, it need to go to first byte, then it need to go to second byte also. So memory addressing is difficult in the case of these type of data storage, because the data is spread across different bytes. So normally most of the processes, they are using byte addressing, means the data will be taken from first byte, then second byte, then third byte, in the order the data will be taken. But if the data size is very small, it can be accommodated within that single byte. Otherwise it can be given into the different other set of bytes available within the memory location. So if we are not using byte addressing, there will be more some more operations, extra operations to be done for accessing the data by referring both memory addressing. So it is always better to use byte addressing to access the data from the memory. So that is the importance of memory addressing. So how the memory will be addressed? The simple answer is, memory will be addressed byte by byte. That is a point to be mentioned in the memory addressing. Then comes the addressing modes. Addressing modes, you might have heard about addressing modes when you study different microprocessor architectures like 80, 85 and 86. So here how the memory or register, all these details can be used as part of an instruction, that is called as addressing modes. So how these register and memory can be used with the whether we can directly use memory, whether we can directly use register, whether we can use 2 registers, whether we can use register with some other value, whether we can use a memory address and some other value, all these things. So what are the different ways in which we can access the data with the support of an instruction? That is called as addressing mode. So whatever we write, if you write an example, add a comma b, we need to access the content of a, we need to access the content of b. So that was mentioned in the previous case, that is memory addressing, how it can be addressed. Now how we can write that? For adding a and b, I am using a one register, b another register. So in which format we are using that instruction? That is called as addressing modes. So in the addressing modes, we are sometimes specifying registers, various registers we are specifying. Sometimes we will be mentioning the constants like immediate values, or sometimes we will be referring the address of memory. So addressing mode, within the instruction we need to specify either registers, the constants, or the memory address. Now some examples taken from Mips architecture. The various addressing modes used are register addressing mode, immediate addressing mode, and displacement addressing mode. Register addressing mode, where we use registers. Immediate addressing mode, where we use some immediate value along with the register. Displacement, within the register, with register we are also specifying the offset or displacement for getting the exact location of a particular data. For getting the exact location of a particular data, we are using an additional displacement information also. Then 80x86 uses some more addressing modes along with register, immediate and displacement. So it also uses register, immediate and displacement. It also uses absolute addressing mode, then based indexed with displacement, based with scaled index and displacement. So some additional features are also being added to the processor 80x86 for making this, or with the instruction we are having several other options for creating the addressing modes of the instructions used with 80x86. In the next slide we will look at some of the examples. So you will see what are these additional based indexed with displacement, based with scaled index and displacement, etc. We will look into this not in detail. We will just look at the sample instructions used with some of these processes in the next slide. So we will look at each addressing mode and we will see some examples. First one is register. As the name indicates, register addressing mode. Register addressing modes on example is given like add R4, R3. R4 is a register, R3 is another register. So the meaning will be like the content of R4 will be added with content of R3 and the result is stored in R4. Result is stored in the in many instruction, the first operand means first register will be the destination where the result will be stored. In some architecture they are using a register exclusively for storing the result other than the operands used, but many instruction architecture uses this format where the first register will be the target or destination register where the result of the operation will be stored. Then second one is immediate addressing mode, where you can see add R4 comma a constant value. Just for indicating it as a constant, it is using hash. So what will happen? The content of R will be added with the value 3 and the result is stored in register R4. So it is for constants. Then third one is displacement. An offset will be added with the register content. So add R4 comma 100 R1. The meaning is the content of R4 will be added with the memory content of register content R1 plus 100. So register R1 is having a value available. With that value, an offset 100 will be added. Then we are getting another value. That memory address, there will be some value. That value will be added with register R4 and the result will be stored in register R4. So the content of register is actually the base address. Into that the offset will be added, will get the exact address, and that address value, the memory content of that address will be added with the register content R4 and the result is stored in R4. That is displacement. The next one is register indirect. Register indirect. See, add R4 comma R1. R1 is given within bracket. So look at the meaning of this statement. Register R4. The content of R4 will be added with R1 within bracket. Means register R1 consists of a value. That value is actually an address of another data. So the memory content of the address value that is given in R1, which is equivalent to pointer. You can think about pointers in C, where a pointer points to, means it is actually what is a pointer actually, which points to the address of another variable, right? Similarly here register R1 consists of a value, that is the address, and that address consists of a value, the memory content of that address. So indirectly we are getting the value. That is why it is called as register indirect. The next one is indexed. Indexed. What is the difference here? Almost same thing. Add R3 comma within the bracket R1 plus R2. Let us see what will happen here. It is actually used with arrays, where we are having base address of array and index. So this is the base address and this is the index value. So what will happen? The memory of register R1 means register R1, the content of register R1 will be added with register content of R2. Then we are having that address that is for array, array from 0, 1, etc, etc. This is the way how we are dealing with array 0, 1, 2. So if I want to move to some other index location, the with base address, that index amount will be added. Okay, so base address and index amount will be added. That memory content, that address, that value will be added with R3 and the result is stored in R3. That is called as indexed. It is used for array access. Then direct or absolute, that is another addressing mode where the direct memory address can be given. So add R1 comma within the bracket 1001, which is the memory address. So what is the meaning of this? The content of register R1 will be added with the memory content of 1001. So directly this memory content will be added with register R1 and the result is stored in register R1. Then another example is memory indirect addressing mode. So here you can see add R1 comma to indicate memory indirect. Within the bracket we are specifying the register, but we are using an @ symbol here. The meaning is it is also similar to pointer. I will see memory indirect. So register R1 will be added with, so what is this? Register R3 we are having a value, the content of that value, memory. So that register is having a memory address, that memory content which is another address. That memory means memory means indirection. Pointer we are using an indirection operator, right? So one address consists of address of another variable. Normally the address consists of means a pointer consists of an address of another variable, but now the pointer consists of address of another address. That address will be having a value. So indirectly we are accessing a particular element. So register is having a memory value, the memory content of that register value, which is again an address. The content of that particular address will be retrieved and that will be added with R1 and the result is stored in register R1. Then auto increment, add R1 comma R2 plus. Look at this format. It's not a very commonly used format, but just understand auto increment and auto decrement. So what will happen here? Register R1 will be added with the memory content of register R2. So register R2 value is an address, that address value, memory content of that value. These two will be added. Then after adding that, the register R2 will be incremented by D. D is a value which is equivalent to the value corresponding to the type of array. It is also used with array. Assume if you use an integer array, normally for earlier system, for integer we require 2 bytes. So when we increment point value, always it is not incremented by 1, it will be incremented by 2. If you are using a floating point array, floating point earlier system we are using 4 bytes. So if you try to increment that pointer variable, it will be incremented by 4 only. That depends on the type. So pointer increment is always it is based on the type of array type. So integer, if it is integer, 2 will be incremented. If it is floating point, 4 will be incremented. So after doing this manipulation, the second register will be incremented by the type size. If it is integer, it will be incremented 2. You can imagine why it is incremented by, because the next value will be after 2 bytes only. Whatever be the size of the first element, the next value will be placed in the means after 2 bytes only. So that value will be, so that D indicates the size of type of array. Similarly, auto decrement. So first of all, it will be decremented by 2. It is also used with not array. It is for stack, push and pop operation. We can use this decrement operation because from the stack we are popping the element, right? We are decrementing. So register will be decremented by the value type of the element. Then the operation register R1 will be added with the content of register R2. That is the not the content of register R2. Content of register R2 is an address. That address memory content will be added with register R1 and the result is stored in R1. So first it will decrement, then the operation will be executed. Then finally we are having a scaled index that I was mentioning in the previous 80x86 architecture. Add R1 comma 100 R2 R3. It's a different operation. Just have a look at this. I don't know whether we can remember all these things, but just for understanding the various categories of addressing modes. Most of the system uses the first 4 or 5 addressing modes. Other addressing modes are also available with several processes. So here add R1 comma, so register R1 will be added with just look at here, register R2 plus 100. So R2 is having a value, with that an offset 100 will be added and that memory content. So R2 will be having an address plus 100, we are getting a new address, that value plus it will be adding the content of R3, then it will be multiplied with the value D, which is the type of the array, which is the size of type of array, which is the size of type of the array. So this is called as scaled indexed addressing mode. So these are the various addressing modes present with various processes, with some examples just for understanding how means what is actually these addressing modes, which is used with many microprocessor architecture. I hope it is clear. Now next point is types and sizes of operands used in the instruction set architecture. So we have taken one example from 80x86, even Mips and ARM. They all support several operand sizes. We can use 8-bit normal ASCII character, that size operands. We can use 16-bit Unicode character or half word Unicode, which is commonly used with Java programming and all, which requires more characters. Then we can use 32-bit integer. Now recent systems are using 32-bit integer, or it is also called as a word. Similarly, 64-bit double word is also being supported by all these processes. Similar to this, we are using two floating point formats. One is IEEE 754 floating point in 32-bit, that is usually called as single precision, and next one is IEEE 754 floating point in 64-bit, which is used for double precision floating point numbers. So these are the different types like ASCII character, Unicode integer type, double type, floating point to single precision, and double precision for simple floating point values, and larger floating point values we are using single precision and double precision. And the sizes for ASCII we uses 8 bits, Unicode 16 bits, integer or word we are using 32 bit, double word or long integer we use 64 bit, for single precision floating point we use 32 bit, for double precision we are using 64 bit size for the operands. All these are just a comparison only, just generally what are the different types and sizes of operands used with various instruction sets. Now 80x86 also supports an 80-bit floating point type, that is an extended double precision. Even larger numbers can also be represented in 80x86 microprocessor. So these are about the different types and sizes of operands used with various instructions available in different processes. So I will stop it here now. We have seen the basics, first different major elements to be discussed on the instruction set architecture. The remaining portions like operations and other parts of instruction set architecture will be discussed in the next session. Hope it is clear, and let's have a look on to the video once again, so that if any portion is missing or if it is difficult, you can have a look on to the video once again. Thank you.